In our last video, we completed the sliding window pattern and saw how maintaining a rolling continuous chunk lets us process subarrays in pure O(n) linear time. Up until now, our core focus has been optimizing scans, whether that's using hash maps to cache state, two pointers to squeeze inwards from opposite edges, or sliding windows to track moving subintervals. These patterns are absolute lifesavers when you have to touch your data. But what happens when you don't actually need to inspect every single element to find what you're looking for? Say you're looking up a specific user ID, querying a configuration key, or retrieving a metric entry from a massive timestamped database. If you use a standard loop to scan from index 0 all the way to the end, you are logged into an O(n) time complexity. If your dataset contains 100 items, it's practically instant. But if you're querying a live transaction ledger with 100 million records, your application will sit there, lock up CPU cycles, and waste memory bandwidth checking completely irrelevant elements one by one. This is where we need a completely different approach. Today, we are diving into binary search. Instead of scanning linearly, we leverage a massive architectural cheat code, structural order. If your data is already sorted, checking every element isn't just slow, it is mathematically lazy. With binary search, we look right at the middle element, evaluate it against our target, and throw away half our remaining search space in a single operation. This simple trick drops your time complexity from a grueling linear climb down to an ultra efficient logarithmic O of log n performance curve. Think about data indexing. When you write an SQL query or call a find operation in MongoDB on an indexed field like a user ID or created at timestamp, the database engine isn't raw scanning your storage drive. It's traversing a B-tree structure. At its absolute core, navigating an index is just a multi-way binary search. The database evaluates a key, completely discards massive branches of irrelevant data blocks, and homes in on your exact record out of billions in microseconds. You also see this embedded in Git's debugging toolkit. When a production app introduces a critical bug and nobody knows which commit caused it, engineers don't check hundreds of merges one by one. They run git bisect. Git performs a binary search on your commit history. It splits your timeline in half, asks you to test if the bug exists there, and instantly eliminates dozens of commits from investigation. You locate the exact breaking change in like 7 steps instead of 70. So, how do you spot a situation where you should deploy this? Again, the definitive non negotiable trigger phrase is sorted sequence. If a problem space guarantees that your array or list is ordered, or if you can sort it out yourself within an acceptable time bound, your brain should instantly click into binary search. You might also see it manifest as searching for a threshold, like finding the first bad version or the minimum allocation size. The core architectural rule to remember here is divide and discard. You are adjusting the boundary markers, left and right, to isolate the middle index, evaluating the match, and then shifting a border to invalidate half the array. Let us look at a code example to see how this prevents your app from melting under a heavy data load. Imagine you're building a lookup utility for an inventory tracking system, and you need to find the index of a specific item ID within a massive sorted list. If you write a standard linear search, your code is going to look like this. Again, this works fine for minor arrays. But if this function is hit thousands of times a second across a ledger of million items, the server's CPU utilization will spike through the roof because the worst case scenario requires checking every single item. Now let us write the optimized binary search implementation to ensure we only look at a tiny fraction of the data. Let us trace exactly how this function executes step by step. Suppose we pass our function a sorted array of IDs and we are searching for the target 13. When the function initializes, left pointer points to index 0 and right points to index 7. During the first iteration, the loop calculates the middle pointer, that is index 3. Now index 3 holds the value 7. Is 7 our target? No. Since our target is 13, which is greater than 7, and our data is sorted, we know that 13 cannot exist anywhere to the left of 7. So we completely throw away indices 0 through 3. We update that left is equal to mid plus 1, which shifts our left pointer to index 4. During the second iteration, we recalculate our middle pointer for the remaining subarray, which evaluates to the index 5. Now the index 5 holds the value 13. Is 13 our target? Yes. The conditional hits a direct match, and the function immediately returns index 5. Look at the efficiency difference here. A linear scan would have taken 6 operations to find 13, but the binary search found it in exactly 2 steps. If this array scaled up to 4 billion elements, a linear scan could take 4 billion checks. But a binary search would find the element or determine it doesn't exist in at most 32 steps. The dataset grew by a factor of billions, but your processing footprint barely cracked double digits. When you know how to leverage order and structure to eliminate non-viable paths, you stop writing brute force scripts and start designing systems that scale predictably. Across this series, we have built up an incredible foundation. Let us revise them one by one. It is hash map for O of 1 key value lookups at the cost of extra space. Next is 2 pointers for scanning pre-sorted linear collections with 0 extra RAM. Sliding windows for continuously evaluating moving chunks without redundant inner loops. And finally, binary search for cutting ordered search spaces down in logarithmic time. In our next video, we are going to pivot to structural recursion and hierarchy as we take on recursion and DFS, that is, depth first search. We'll examine how to traverse dynamic tree structures, handle call stacks safely, and solve complex decision tree problems without running into stack overflows. As always, the resources are linked right down in the description below. See you in the next one.